The final vector subspace that we associate to a matrix is called the column space of the matrix. Now you might guess from the name that much like the row space, having been defined as the span of the row vectors, you might guess, and you'd be right, that the column space is defined as the span of the column vectors of the matrix. And again, we might speculate as to whether a seemingly arbitrary construction like this would be at all interesting. And it turns out that it is. We'll see many applications of the column space later on, but there are some quick ones that we're going to see right now. First, a little bit of a disappointment. Row operations, we were very pleased to find, preserve the row space of a matrix. Do all the row operations that you want. Take the matrix all the way down to reduced row echelon form. The row space doesn't change, and that was wonderful, and we used that as a tool to find a basis for the row space. This is not true for the column space. Row operations do not preserve the column space, and that's why we have to accept this is bad news and it's a disappointment. But there's some good news, and that is that row operations do preserve something different. Relations between the column vectors. Not the span of the column vectors, but the relations between the column vectors. Let's see an example. Here's a matrix. Here I've done a row operation to get down to another matrix. And at a glance, let's first observe that we have not preserved the column space. Let's look at these column vectors originally. Both of these column vectors are in the direction of the vector 1, 2. So the span of those vectors is a line that points in the direction of the vector 1, 2. Every linear combination of these columns is in the direction of 1, 2. And it's immediately clear that that's not the case down here. All of these vectors in the direction of the vector 1, 3. It's just a different direction. Okay, so the column space has clearly changed. But we have preserved relations between the column vectors. So you'll notice, for example, looking at these two columns, there's a relation in that the third vector, the second vector is 3 times the first vector, thus giving us this relation between the column vectors. And even though these columns are different, that exact same relation holds between those two columns. The second column is 3 times the first column. So the relations between the columns are preserved. Okay, it's not immediately clear how we're going to use that as a computational tool, but it's going to turn out. So let's first prove this result. Here's the theorem. If you have a relation between the columns of A, then that is also a relation between the columns of EA. In other words, doing an elementary row operation does not change those relations. This is a wonderful little proof, simply taking advantage of what we know about matrix multiplication and relations. Let's remind ourselves, what is a relation between the columns of A? Well, a relation between the columns of A is a linear combination of the columns that equals 0. And I have to ask myself then, where have I heard this expression, linear combination of the columns? Where else have we heard that? Well, a linear combination of the columns is one of our interpretations of a matrix vector product. So specifically then, this matrix vector product, this is a linear combination of the columns of A. And therefore, this is a linear combination of the columns of A that equals 0. Therefore, that is a relation between the columns of A. Wonderfully, we can express a relation between the columns of A simply by a matrix multiplication. Very nice. And then likewise, this is a relation between the columns of EA. So if we want to show that these relations are preserved, all I have to show is that if I have coefficients, if I have a vector of coefficient C that makes this equal to 0, then that same vector of coefficients would make this equal to 0. In other words, I just have to show that these two statements are equivalent. And that's a very easy algebraic task, because all I have to do to show that that implies that is multiply on the left by the invertible elementary matrix E, and to show it goes the other way, I multiply by the inverse of the invertible elementary matrix E. So very convenient algebra. It's wonderful little proof. Again, all taking advantage of the fact that we have an interpretation of the matrix vector product as a linear combination of columns. Very nice. Okay, now how do we find a basis for a column space? I'm going to start with an example of a reduced row echelon form matrix. So we're going to start by looking at the column space of this reduced row echelon form matrix. We'll worry about A itself later. Starting with this reduced row echelon form matrix, I claim that this first pair of vectors here is a basis for the column space. And this isn't hard to see. You can look at these vectors and persuade yourself that this is the case. Look at these two vectors. I observe that this is a linear combination of those two yellow vectors. You at a glance can see what those coefficients are. That would make that work. Likewise, that is a linear combination of V1 and V2. It's, again, at a glance clear. 5V1 minus 1V2 would create this vector V4. All of these vectors are in the span of V1 and V2. So V1 and V2 span the whole column space. They are also very clearly independent. So, no problem. We see that we have a basis for a column space of a reduced row echelon form. Now, that wasn't our original question. What we would like to know is, how do I find a basis for a column space of any matrix? Well, let's look at the argument that we just made and interpret it a little bit differently. We made the observation that this pair of vectors is independent. Well, notice that statement is a statement about relations between the columns of the reduced row echelon form matrix that we're looking at. It's a statement about relations between columns. Okay. Now, this assertion that these vectors span the column space. Okay, well, saying that they span the column space, we can first argue that V3 is a linear combination of V1 and V2, so is V4, so is V5, and then I could further argue that any linear combination of the columns, by taking these formulas, plugging them in, would give me a linear combination of V1 and V2. And if I were to take this and move it over to the other side of the equation, note that that is also a statement about relations between columns. So everything that I need to know, to show that this pair of vectors here is a basis for that column space, is a statement about relations between columns. And wonderfully, relations between columns are preserved when you do row operations. And that's the foot in the door. That's how we actually turn this into a computational method. Because whatever relations hold for the columns of the reduced row echelon form, the same relations hold for the columns of A. So in this case, going back up here, these vectors were a basis for the column space of the reduced row echelon form, and therefore the corresponding original column vectors are a basis for the column space of A. And this is expressed in this theorem right here. The columns of A corresponding to pivot columns of the reduced row echelon form a basis for the column space. Let's see an example. Here's a matrix. Suppose I want to find a basis for the column space. Well, row reduce it. Step 1, row reduce the matrix. Identify where your pivots are. There's a pivot. There's a pivot. And this theorem says, look at the columns of A that correspond to where the pivots are. So critically, columns of A, not columns of the reduced echelon form, columns of A. So that's where my pivots are. So the corresponding columns of A are a basis for the column space of A. It's a wonderful little method. So let me summarize now with this computation having been done. When you've done a row reduction, you identify where the pivots are. The corresponding rows of the reduced echelon form are a basis for your row space. The corresponding columns are a basis for your column space. All from one row reduction. Okay, get two bases out of one calculation. Okay. Now, the book makes an observation that, and this is a really easy argument to follow, the column space of a matrix, well, if you were to take that matrix and transpose it, the columns would become rows, and so the columns of A are exactly just rows of A transpose, and so the span of the columns of A is the span of the rows of A transpose. And hey, we already know how to find a basis for a row space. So the book's suggestion is take your matrix, transpose it, and use the existing algorithm for finding a basis for the row space. The trouble is, in order to do that, you have to row reduce A transpose. And the row reduction of A transpose at a glance is not related to the row reduction of A itself. So the difficulty that comes from the book's strategy here is, even though it's really easy to follow the argument, the calculation is going to be twice as difficult. You will have to do two completely separate row reductions to get your two bases. Using this method, you only have to do one row reduction, just the one row reduction, and you get two bases all at once. Okay, one last observation. We saw previously that the dimension of the row space of the matrix is equal to the rank. Now we see that the dimension of the column space is equal to the rank. You can see that right here in this process, that both the dimension of the row space and the dimension of the column space, both of these dimensions correspond perfectly with how many pivots do you have. You get one dimension for each pivot. Therefore, the dimensions are the rank. And that's nice. Even more than that, you might say, a different point of view you might take on that, is that the row space and the column space always have the same dimension. And that's really intuitively surprising, I think. I'll come back up here to this original matrix. It would seem very tempting to look at a highly non-square matrix like this and say, well, this is an opportunity to make a column space whose dimension is greater than the row space. After all, there are only 3 row vectors. That means that the dimension of the row space could be at most 3. There's no way the row space is going to be more than 3-dimensional. But look, we've got 5 column vectors. Surely I could arrange for these vectors, as 5 of them, to maybe span more than 3 dimensions. And then you realize, well, but they can't span more than 3 dimensions because each one of them is 3-dimensional inside of, therefore, this 3-dimensional vector space called R3. But it just seems like there ought to be some sort of wiggle room in there somewhere. And amazingly, there isn't. These dimensions are always the same.